Now that you're here, we have both of our live camps with us as well. We have Brantford, can give a wave, Brantford, and we have St. Thomas as well.
Awesome.
So
Great.
welcome. Yeah, welcome everyone. So let's get started. Just a moment here. Oops. All right, so we also have our camps across Ontario watching the live stream as well. And so I'll introduce you to everyone watching on the live stream. So
Okay.
welcome everyone. We have Dr. Elise Fear here with us today, and she's a professor in the Department of Electrical and Computer Engineering at the University of Calgary. And as I mentioned, we have Brantford and St. Thomas camps joining us. So welcome everyone. As you know, today's Physics Day at STEM Camp. And campers are experimenting with basic forces, simple machines, using gears, levers, screws, inclined planes, pulleys, wheels, and axles, a whole bunch of different things they're experimenting with, which is awesome. And I know the campers are going to have lots of questions related to their various physics challenges, all the simple machines they're building. But first, Dr. Fear, I'll go to you. Can you, introduce yourself and tell us a little bit more about what you do at the University of Calgary?
Sure, I'd be happy to. So it's true that my name actually is Dr. Fear, which sometimes makes me feel like I must be some kind of supervillain or something, but maybe I'm actually not. I'm not sure. I'm still working on it, trying to figure out what my identity will be as a supervillain. But for now, I am a professor at the University of Calgary, and I have a daughter who's probably around the same age as you are in the camps. And I asked her last night, I was talking to her about this, and I said, well, what should I tell them about what I do? And she said that I should tell you that I work with a super cool team of researchers and we're trying to help people. And I thought, you know what, that's a pretty good summary of what it is that I do at the university. So as a professor, I do a couple of different things in my job. One thing I do is I teach classes. So I have courses that I run for our undergraduate and our graduate students here at the university. And then there's a lot of things that you have to do that are basically going to meetings, sitting on committees, reviewing grant proposals, those sorts of things. So I do a fair bit of that as well. But the main thing that I really love to do is research. And I have a team of students that helps me with this research. And together we're trying to come up with a new way of imaging. So we're interested in coming up with a way of taking pictures of the inside of the body using microwaves. So we're not using microwaves like you have in your kitchen for cooking. We're using much lower power microwaves. So these microwaves don't actually do any heating. So what we're interested in doing is coming up with a sort of map of how the properties in the body change. So with x-rays, has anyone ever had an x-ray before? If you've broken a bone or something like that? All right, so if you have had an x-ray done, x-rays, they look at really little details. They're really good at seeing if you've got a break in the bone, and they tend to look at a certain property of the tissue, like density of the tissue. But with microwaves, we're actually looking at water. So we're looking at how much water a different tissue has. So if you think about different tissues in the body, muscle, for example, has a lot of water in it. So your heart would have a lot of water in it. Blood obviously has a lot of water in it. Bone doesn't have very much water in it. And fat doesn't have very much water. So we can make maps that show where these different tissues are in the body. So that's what my team is trying to do. So when we make these maps, we have to do pretty much everything in our lab because the kind of imaging we're doing, the kind of pictures we're trying to make, there aren't machines out there already to make these kinds of pictures. Instead, we have to build them. So we do pretty much everything with building the machine. So one thing we need to do, we're using microwaves, so we have to send microwaves to the tissue and then detect reflection. So we're kind of sending a signal, we're pinging the tissue, and we want to see what comes back. So we have to actually design sensors. So I've got one here. This is one that we designed in my lab. So this is a special sensor that we'd use in the scanner that we developed And basically what it does is it would be positioned something like this, maybe in contact with, like you could see in contact with your arm, let's say. And then we would put waves in at this end, and they would come out the other end, and then they would, this is kind of tricky with this, I should have practiced this. And then we might have a model, let's say, so this might be a piece of tissue. So you could see that we would have the sensor in contact with the tissue, and then we would record a reflection from it, and that would be what we'd use to make the image. Now, if I have this piece of, this object that I want to scan, if I just take one measurement here, that's probably not going to be enough. So I have to figure out a way to kind of turn this and scan the sensor all around the object. So my team has done a lot of work as well, developing the machine to actually take one of these little sensors here. And they might also look something like this. This is another sensor that we might design. So we actually have to come up with a machine so that we can take this sensor and scan it all around that object. So we don't just look at these little reflections, we also have to build the machines that allow us to basically get the measurements we need to form an image. And we also have to figure out how we can have people lie on the machines so that we can scan the tissue we want to scan. So for example, if I was just scanning someone's arm, that might be pretty easy to do because I could just, have my arm here and then scan. But usually I need to know where this thing actually is in space. I can't just say, oh, I did a scan like this. I actually need to know where this was when I was collecting data. So we spend a lot of time making these machines to actually collect all these signals. And then once we've collected the signals, we have to make images out of them. So we also spend a lot of time taking the signals and figuring out how we can come up with sort of a map of the tissues inside the body. So that's kind of what my group does for the research that we do. And because we're doing biomedical research, so we're interested in not only building these machines, but actually scanning people. We also work with doctors over at the hospital. So we go over to the hospital and make sure that we're making machines that make sense to the doctors. And they also help us by inviting patients to come to my research lab and get scanned so we can see how well our machines work.
Wow, that sounds like some really interesting research, and sounds like you have some experience building complex machines, which might be very helpful helping our campers with their simple machines today. So let's get started with a few questions from the campers. Was there a question in St. Thomas for Dr. Fear today? Go ahead, Jolie.
Yes. What is physics?
What is physics? That's a really good question. So when I think of what physics is, I think of it as the study of the world around us. And with physics, I often think about all kinds of different things. We want to understand how things move through space. We want to understand how, for example, if you have a cell phone, how you can talk to your friend. So when that happens, there's waves moving through space. So we're often interested in physics in looking at different forces and energies and fields and figuring out how those interact with the world around us. Does that make sense?
I think so. I was waiting to hear from St. Thomas. That was a good question to start things off with. Thanks. How about in Brantford? Was there a question we could go to in Brantford?
Yes, Sydney has a question.
Why do we
Hi.
move? Why do we move? Why do we move the way we move?
Why do we move the way we move? That's a good question. So when I think about why we move the way we move, I've had some pretty interesting chats with some of my friends over at the medical school about this. I know some people who actually spend a lot of time figuring out why we move the way we move. And they look at all kinds of things like how our body is put together. So when we have a thought of, oh, I want to walk from here to Tim Hortons to get a hot chocolate or something like that, then we need to be able to have nerves fire to move our muscles. So there's a whole complicated system. Our bodies are almost like machines in a way. There's a whole complicated system that works together to get our muscles to move and to move our bones and to get us from one place to another. There's a lot of people who study exactly how it is that we walk and why we walk the way that we do. And is actually, my understanding is it's a lot about energy. So you'll walk in a way that gives you the biggest bang for your buck, in a sense, that'll get you the furthest while you're putting out the least amount of energy. So our bodies are smart, really smart. That's one thing that I've learned.
Yes, a smart machine. That was a good question too. Wow. So I'm going to go to our first question from Twitter. This is from our camp in Ingersoll. Hello, Ingersoll. They want to know, what is a Gforce?
What is a Gforce? That's a good question. So I don't do much kind of space research, but I think Gforce is usually gravitational force. And if you're moving extremely quickly, like I'm thinking about test flights and that sort of thing, because I know that people would talk about being at a couple of Gs. So when you're moving extremely quickly, sometimes you can experience forces that are more than the gravitational force that you'd experience on Earth. And I think that's what G-force would refer to, but I'm not really an expert on that.
Okay, thanks. Another question on Twitter from our camp in Dundas. Hi, Dundas. About microwaves. So they want to know, if something has no water in it, will it still heat up in a microwave?
Something has no water in it will still. Well, I think if we look at some examples, I'm just thinking back to when I was a PhD student, and we had a research engineer in my lab, and he used to like to put CDs in microwaves. It was disgusting. I don't recommend that you do this because the smell is unbelievable, but let me tell you, those CDs heated up. So metal does tend to heat up in microwaves as well, so it's not just water, there are other things that heat up too.
Okay, but not recommended to do.
Absolutely not recommended to do, but I'm just remembering there was sparks and smoke, and it was quite dramatic. I'm not sure why he decided to do that, but that's always the example I think about.
Yeah. All right, another one from Twitter from our camp in Tilsonburg. They want to know, how does air move a windmill?
How does air move a windmill? That's a good question as well. So I think it's I'm thinking about going down south in Alberta where we have farms of windmills. I'm not sure if you have that in your part of Ontario as well, but we have in a really windy part of the province, there's tons and tons and tons and tons of windmills, and they're absolutely huge. So I think what happens is the blades are designed in a special way so that when the wind, the air kind of pushes on the blade, it causes it to move. So it's basically, I think it's pressure on the blade that causes it to move.
Okay. Let's go to one of our live camps, maybe back to St. Thomas. Was there another question for Dr. Fear in St. Thomas?
Yes. How does gravity work?
How does gravity work? That's a good question. I'm just trying to think if I can explain that one. That's a really good question. I have different ways of thinking about how gravity works. And one way I would think about it is the Earth is a really, really, really big object, and it attracts other objects to it. And I think that you can almost think about yourself being attracted to the Earth, and that is kind of how gravity works in a sense. I don't think that's a very good explanation though, because I haven't thought about how gravity works for a long time. So I'm going to have to think about that.
Yeah, good question for the expert today. Thanks. How about Brantford? Can we go back to Brantford for a question?
Yep.
Hi.
Right there.
Hi, I have a question about how animals move. How would four-legged animals go about moving without stepping on their legs or front paws?
That is a very good question as well. Now, how would they go about moving? I think it has to do with how all of the parts of their bodies communicate with one another. Um, Certainly at the University of Calgary, I know of researchers who study how animals walk, but they usually look at how animals walk after they have an injury in their leg to figure out how their walk changes. But I think, as we talked about before, it's a lot about your body working together. So those messages going from your brain through your nerves to get your muscles firing. And apparently, the researcher I mentioned before who was looking at walking, he actually was looking at cats before he was looking at humans. So I think a lot of the ways that our brain works to move our muscles, I think that's fairly similar with animals as well as humans.
Okay, thank you.
Great. So we have another question, getting back to machines, a question from our camp in Dundas. They want to know, what's the most important part of the engine? For example, maybe in the machines that you've been building.
So in the machines that we're building, we don't exactly have an engine, but we have motors. So we have a lot of motors to move the parts of the machine around, and I would say that those are the most important parts of our machine. So we actually have, with our little sensor here, it actually moves in a bunch of different ways. So it moves up and down, it moves around, it moves in and out, and it kind of tilts like this. And we have motors to make it tilt. We have motors to do the up and down and the around and the back and forth. So without all of those motors, we really couldn't move this as effectively as we do.
Okay. And also related to your research, a question from our camp in Sudbury. They want to know, why is it important to study the tissues in the body?
Well, that's a really good question, and it's actually something that people have been interested in for a really long time. It's not a new thing. People have been interested in it for over 100 years. A couple of different reasons to do it. Nowadays, we have more and more exposure to fields through things like cell phones. And when people are designing new devices that are used near people, they actually have to look at safe operation of those devices. So if we don't understand what the properties of the tissues are, then we can't make models to let us sort out whether or not, say, a cell phone radiates low enough power that we don't need to be very concerned about it.
Oh, interesting. Thank you for that question, Sudbury. That's a good question. Did I see another question in Brantford? It looked like there was a curious camper there, perhaps. Hi.
How does a pulley pull stuff up?
How does a pulley pull stuff up?
Over this way. There you go. Now you can see.
So if you had a pulley kind of like this and you attached load to it with a rope, and then you would pull on the other end of the rope, is that the kind of question you have?
Yeah.
So that's a good question, and I think the way that it happens is the pulley usually has a wheel in it that turns, and because you're pulling on the opposite side of the load, you have a little bit more leverage with a pulley. Then I think leverage is not exactly the right word because it's not really a lever, but I think I haven't thought about pulleys for a while either. We don't really use them in the machine that I'm developing, but I think it's just basically a way to transfer energy more efficiently.
All right. Thanks for your question. Thank you. So we're coming to the end of our time with Dr. Fear, but maybe there's one last question we can end with in St. Thomas.
How does gravity stay in place?
How does gravity stay in place? Sorry, I was having a little trouble hearing. Is that the right question?
Could you repeat the question, please?
How does the atmosphere stay in place? How does the atmosphere stay in place?
Well, how does the atmosphere stay in place? So I think actually that has to do with gravity as well. Um, so I have some colleagues over in physics, in the physics department here, and they study the atmosphere, and they actually send rockets up into the atmosphere to record different features of it because we're trying to understand things like space weather. What's the weather in outer space and how does that impact Earth? But I think the atmosphere, my understanding is it stays in place because of gravity, because of the gravitational forces around the Earth.
Great. Thank you very much, Dr. Fear, for answering all our different questions. There were a lot of different topics covered today, so thank you very much. And thanks to all our campers out there for all the great questions. Thanks.
Well, thanks everyone, and I hope you enjoy the rest of your week in STEM camp.
Awesome. Thank you very much, Dr. Fear. Have a great day.
You too. Thanks. Bye.
Thanks. Bye, everyone. Bye.